We're going to prove property 4 of theorem 6.2. And to prove property 4, we're going to assume that we know that 1, 2, and 3 are true. So let's assume we have proven these already. And we're going to use them to prove the next one, property 4. And so property 4 says the order of A is equal to the order of phi of A for all elements in A. So you can also rephrase this property as saying that isomorphisms preserve the order of elements. Okay, let's prove that. So we wanted to prove 6.2 property 4. So that was isomorphisms, preserve order of elements. Okay. So let's say for some n and z, we have that a to the n is equal to e. Then, if we apply the isomorphism to this equality, we get that phi of a to the n is equal to phi of e. And that is true because phi is 1 to 1. So this we know because phi is 1 to 1. But from property 1 that we proved in the previous video and property 2, on the right hand side, phi of e, that is e bar. So that is property 1. And on the left-hand side, phi of a to the n is the same as phi of a, that whole thing raised to the n. That is property 2 of theorem 6.2. And so now we have this nice relationship. I'm going to write it down in red because we're going to refer to it quite a bit. So we have a to the n is equal to e if and only if phi of a, that whole thing to the n, is equal to e bar. And so far, we're not saying that the order of a is n or anything like that. We're just saying that if a power of an element in G is the identity, then it's also true that the same power of the image in G bar is equal to the identity, and vice versa. So we have that if and only if, and I'm going to call this if and only if fact star. I'm going to give it a name. We are going to use that in our proof. Now, looking at this, we really, when we are now working with the orders, we have two cases. Case one, what if the order of A is infinite? So case 1, the order of A is infinite. We can actually say if and only if the order of phi of A is infinite. Because of that if and only if that we just said. So a to the n is equal to e if and only if phi of a to the n is equal to e bar. Now assume the order is infinite, then a to the n is never going to be equal to e. That gives you an if and only if with phi of a to the n is never going to be equal to e bar. So because of this if and only if statement star, we have that a is infinite if and only if phi of a is infinite. So our statement is already true for the infinite case. Now, our second case is what if the order of A is finite? Well, that's also if and only if. It's the same statement, really. It's a negation. So we have phi of A, the order of phi of A is finite. Because of our statement star. But now we actually have to prove something. So now we actually have to prove that the order of A is the same as the order of phi of A. There's some work to do here. Okay, so suppose that the order of A and the order of phi of A are both finite. So let's give the orders names. So let's say the order of A is n, and the order of phi of A is m. And we don't know what they are right now, but so what our job right here is to show that m is equal to n. That's what we need to do. Okay, let's see how we can do that. So we know that A to the n is equal to E implies that phi of A to the n is equal to E bar. That is by our equivalent statement star. But that means that the order of phi, which we called m, that is the order of phi, is less or equal to n. Because if phi of A to the n is equal to E bar, then n, either it's the order or it's a multiple of the order. But in any case, m, which we called the order of phi of A, is less or equal to n. And we also can start with the other statement. We can start with, what about phi of A to the m being equal to E? So we know that is true. Well, the order of phi of A we called m, so we know that phi of A to the m is equal to E. But that then implies that A to the m is equal to E by our statement star. And that gives us the opposite inequality. So that means that the order, that n, which is the order of A to the n, of the order of A, is less or equal to m by the same reasoning. If A to the m is equal to E and the order of A is n, then the order is less than any power that makes, less or equal to any power that makes A to the m equal to E. So now we have these two inequalities right here. We have that m is less or equal to n and n is less or equal to m. That can only both be true if m is equal to n. And that's what we wanted to prove. So that is the end of our proof. So this shows that the order of A is equal to the order of phi of A.